Hello and welcome. This is Cambridge O-Level Chemistry paper number 2. The subject code is 5070. This is paper number 2, version 1 of May-June 2022. Let's start. Section A, it says answer all the questions in this section in the spaces provided. The total marks for this section is 45. Question number 1, choose from the list of compounds to answer the question. So there is a list of compounds that are given to us. It also says that each compound may be used once or more than once or not at all. So let's see what questions are there. State which compound, part A, reacts with dilute nitric acid to form a gas that turns lime water milky. So remember the test for a gas that turns lime water milky is carbon dioxide gas. So any compound that contains a carbonate that will react with nitric acid to form this carbon dioxide gas. So in the list, find a carbonate salt. So we have sodium carbonate. So our answer will be Na2CO3. So remember, the reaction would look something like this: Na2CO3 plus HNO3. That will give us nitrate salt, sodium nitrate, NaNO3 plus H2O plus CO2. You can always balance the equation. So for example, like this, something like this, you can always balance it. Then remember part 2, react or state a compound that reacts with warm aqueous sodium hydroxide to form a gas that turns damp red litmus paper blue. So remember, a test for an acid is blue litmus turning red. So this is not an acidic gas. That will be something more on a basic or an basic side. And basically, this is a test for ammonia gas or NH3 gas. So any salt that contains NH4 or NH4 sort of compounds, that will be or the ammonium salt in amongst these. So for the first one, ammonium chloride, that will be the one that will react with sodium hydroxide to give us ammonia, sodium chloride, and H2O. So the answer will be an H4Cl. Remember, the reaction will look something like this: NaOH plus NH4Cl. It will give us NaCl plus H2O plus ammonia gas. Again, I'm not balancing it. I'm just saying that what would be the reactants or what would be the reactants after this reaction. So part C, it says reacts with dilute hydrochloric acid to give a gas that decolorizes acidified potassium manganate. So this is the test for sulfur dioxide gas. So any sulfate in the group that is, you can say, that reacts with dilute sulfuric acid or means that is soluble. So we have one sulfate, we have two, and we have three sulfates. And the best answer for this is potassium sulfate because that is a most soluble sulfate we get. So K2SO3 will be the best choice for this case. Next part, it says part D. So the compound is prepared during precipitation reaction. So remember, all nitrates are soluble. So nitrates never use a nitrate here. So nitrates are soluble. Generally, if we have either carbonates or sulfates are insoluble. Potassium sulfate is somewhat soluble, but zinc sulfate and barium sulfate. So the best choice amongst zinc and barium would be barium sulfate. Barium sulfate. Then it says contained an anion with a charge of plus or of -3. So remember, PO4 3 negative is a good anion. So find something like this. So yes, this is one we have here. So sodium uh, salt, Na3PO4. Then it is used as an oxidizing agent. Famous potassium iodide we have seen here. So this is the famous oxidizing agent, so we can use it here. So this is how we are going to solve our first question. So remember the test for an oxidizing agent, that the color change from colorless to brown. So this is a colorless salt as an oxidizing agent. When it says so the iodine is removed, so we'll get the complete iodine. That is a test for an oxidizing agent. So moving ahead, question number 2, it says the table shows some information about elements in group 5. So the elements are nitrogen, phosphorus, arsenic, antimony, and we can see that the final, the electronic configuration, the final, the valence shell have, or the valence shell has around 5 electrons, all of them. And then there are some melting points. So the melting point, we can see that the melting point increases and then increases a lot, and then suddenly decreases. And same is or more or less the trend with boiling point, but it basically boiling point increases and it keeps on increasing as we go down the group. So the first part, it says the electronic configuration for phosphorus. So for phosphorus, I would just recommend go and check the periodic table at the end of the paper. At the end of the paper, you will find phosphorus as P. There is 15 on the top, 31 at the bottom. So 31 is the mass number, 15 is the electronic or the number of total number of electrons here. So with 15, you can have 2, then 8, and then 5. And if you sum up all this, 2 plus 8, 10, 10 plus 5, 15. So we have a total number of 15 electrons. So the electronic configuration will come as 2, 8, 5. Then part B, it says explain why it is easier to predict the boiling point of bismuth rather than to predict the melting point, rather than to predict its melting point. So with the melting point, we can see that the trend keeps on increasing, then suddenly it decreases here. So we are in a, I mean, we don't know what sort of the temperature or the melting point it would be because of the trend that has shifted over here. But for the boiling point, we can easily see that the trend keeps on increasing. So we know that the boiling point would be something more than 1380 degrees centigrade. So that is the reason why um, we can easily predict. So let's write it down. The boiling point has oh sorry, boiling I haven't has there's a trend that is increasing, increasing as we go down the group. Whereas the melting point, on the other hand, don't have a fixed trend. Whereas the trend in melting point is not clear. So that is a easy way, or that is the reason why we can easily predict the boiling point, whereas we are unable to predict the melting point. So moving ahead, it says use the information from the table, explain why antimony is liquid at 1000 degrees in. So with antimony, we can see that it is 630 and 1380. So if we are going to draw a chart, let's say I'm drawing a chart over here. So this is the increasing temperature. This is 630 degrees centigrade. This is 1380 degrees centigrade. So this thing is gas. This is its boiling point. This is melting point. So this is solid over here. So why antimony is liquid? So at 1000 degrees centigrade, the antimony is at less temperature than its boiling point. That is 1380 degrees centigrade and is above its melting point. Uh, its melting point, that is 630 degrees centigrade. Therefore, it's in liquid state. Okay. Then question number uh, uh, two, part D. It says nitrogen exists in as a nitrogen exists as a diatomic molecule. And two, it says draw the dot and cross diagram to show the bonding of N2. Show only the outer shell electrons. So remember in the electronic configuration we wrote as 285. So with this electronic configuration, we only have 5 number of electrons in the outermost shell. So with N, and we need to have a dot and cross model. So we have to make 2 circles. So let me draw a little bigger ones. Uh, one circle. It's better to have 2 concentric or 2 equal circles with a little overlap. That would be your best choice. So this is one nitrogen atom. This is another nitrogen atom. So I'll be representing this one with dots. So 2 electrons here. These will be with cross, and rest 1, 2, 3, 1x, 2x. So remember the 8, when we have 8 number of electrons in a shell, that the shell becomes stable. So whenever there is a diatomic molecule that is formed, so if these um, number of electrons interact with each other, then the molecule will be stable. So you can see that at a certain instant of time, there will be 2, 3, 5 of these and 3 shared. Similarly, in this molecule, or in this atom, or in this outermost shell, we have 2 of these X, then 3 of these X are shared with 3 of these dots. So that is a dot and cross model for a diatomic molecule of uh, nitrogen. Remember, you have to show this overlap like this, and because this shows that the outermost shell, or in higher end physics, these orbitals are actually overlapping with each other. So that is how you use a dot and cross model to represent this sort of bonding. So moving ahead, it says explain in terms of structure and bonding why nitrogen has a low melting point. So remember, this is a covalent compound. And since it's a diatomic molecule, it has a covalent compound. There are weak intermolecular forces. And since there are weak forces, whenever you have to, break these bonds, the amount of energy required is not very high. And that is why it has a low melting point. Let's write it down. Um, it is a covalent bound with weak intermolecular forces. The energy required to break these bonds is low. Therefore, the melting point is low. Okay. So moving ahead, part E, it says bismuth is a metal. Predict two physical properties of bismuth. So remember, it is a metal. A good physical property of any metal is conductor or of electricity and conductor of heat. And metals are basically, it says good conductor of electricity and good conductor of heat. These are the best two properties of any metal. And whenever you'll write, then you'll be good for that. Also, you can write ductile, malleable, but again, these are the most safest one and most easily understandable. Then part F, it says the volume in decimeter cube. Remember, decimeter cube of 19.2 grams of nitrogen at room temperature and pressure. So it is asking about RTP. Remember, volume of gas at room temperature and pressure. So 1 mole of a gas has, so 1 mole of gas at RTP is 24 dm cube. So moles, number of moles of N2. This becomes 19.2 divided by molecular mass of nitrogen. The molecular mass of nitrogen is 14 plus 14, 28. So the number of moles comes out to be around 0.687 moles. So 1 mole of gas is to around 24 dm cube. So 0.687 moles of nitrogen at room temperature pressure is approximately, and we have to remember, give it to two significant figures. So you'll get 0.687 into 24, and it comes out to be 16.457. So the nearest two significant figures is 16. So the answer will be 16 decimeter cube. So remember, then there is another way of solving it, and that is by using PV equals to nRT formula. So remember, the pressure is in pascals, volume is in meter cube, N is number of moles, R is gas constant, and the gas constant is joule per Kelvin mole. These are the units, and temperature is again in kelvins. So if we have, say for, let me change the color, say, let's blue. So if we have this formula and if we have these values, so we can use this formula to calculate this as well. So let me do it for you for fun. Although if you remember, at room temperature and pressure is this, remember there is a standard temperature and pressure that is a little different than room temperature and pressure. So do not confuse that with this. So we have to find volume. So volume will, from this formula, the volume will be nRT divided by P. So the number of moles we have over here, so number of mole is 0.867. So R, the gas constant in these terms is 8.31. So 8.31. Temperature, room temperature and pressure. So temperature at 25 degrees centigrade in Kelvin 273, it comes out to be 298 kelvins. So it is 298 kelvins, and pressure in pascals. So the room at 1 atm, so 1 atmospheric pressure is 1.01325 into 10 to power 5 pascals. So if I put it like this, 0.1325 into 10 to power 5. So this comes out to be the volume. And this volume will be in is 0.02443 meter cube. And if you're going to convert it into decimeter cube, sorry, number of moles. So assume, say, this is not 0.67, this is 1 mole. Or say, let's say 0.687. So this value will be 0.016457 meter cube, and if you're going to convert into decimeter cube, it would be 16.457 dm cube. And with two significant figures, the answer will be 16. Okay, so these are two ways to solve it. So if you know these values of or PV or equals to nRT and the values of all these constants, or not constants, I would say parameters, or if you know this statement as at room temperature and pressure, a gas is 1 mole of gas is 24 dm cube. If you know these values, either of these statements, you will be able to solve this question pretty easily. So moving ahead, question number 3. It says that the diagram shows some reactions of butanol. So butanol is, remember, alcohol. So a complete combustion of alcohol, remember, it's an organic compound. Complete combustion will result in production of carbon dioxide and water. A gas A will be carbon dioxide, liquid B will be water, H2O. Then incomplete combustion, again incomplete combustion, gas C will be carbon monoxide, liquid will be carbon water. Okay. Then acidified potassium manganate. So remember, this is an oxidizing agent. So this is an oxidizing, or it oxidizes alcohol. So if an alcohol is oxidized, so actually it becomes a boxylic acid. So it's butanol. So butanol becomes butanic acid. Right? So it becomes COOH, and there is the R, or the butane. This whole C4H something, whatever there will be, it will be there. Then heat with ethonic acid. So alcohol plus acid. It is an esterification reaction. Basically, it happens in the presence of a catalyst. So the liquid B and an organic liquid E. So liquid B is water. That is, again, you can also say that the liquid B is from here. So that liquid B is water, and liquid E is an ester. Remember, so we'll see what sort of ester it becomes. So we have butanol, and butanol reacting with ethonic acid. Ethnic acid is CH3COOH. So let's see what this question holds for us. So it says A, B, and C are different compounds. Identify A, B, C. So for A, we have carbon dioxide. For B, we have water. And for C, we have carbon monoxide. Okay. So we have A as carbon dioxide. Right? CO2. We have B as water, H2O. We have carbon monoxide as C, carbon monoxide, CO. And then it says part B, name and draw the structure of D. So remember, the D was butanic acid, or the carboxylic acid, or the butanic acid. The name was butanic acid. So remember, the structure would be R-COOH. So structure, let's write the formula. So formula will be 1, 2, 3, 4, and this 4 comes. So C3H7COOH. So structure, or the formula will be C3H7COOH. This will be the butanic acid, and it will C3CCOOH, H. So these all are H. So this is our desired structural formula of butanic acid. Okay. So moving ahead, and say name and draw the structure of E. So now this is interesting. So E is an esterification reaction. So we know that the alcohol is RCOOH. This is acid, or organic acid. You can say alkyl acid, organic acid. No, I will not write it. Say carboxylic acid. Aha. And then it reacts with alcohol. So alcohol is you can say R, that is the primary part of OH, call it, or and when the bonds are broken or with the ester, you have to form an ester out of it. So the ester becomes something like this. So from the acid side, this OH is removed, and from this side, this thing is removed. So this whole becomes water, and the rest comes or attaches itself. So it says R C O O. This becomes from here. This O comes here. O dash R plus H2O. So this is will be the structure for it. So we have butanic acid here, and we have butanol. This is what it's reacting. No. So no. So this is not butanic acid. So this is ethonic acid that is reacting with. This is ethonic acid. So we have ethonic acid that is reacting with butanol. So ethonic acid is CH3 COOH, I suppose. Yes, CH3 COOH plus butanol. We have C4H9OH. So this becomes actually so first R comes from here. This is the R. So CH3, then COO, then OC 4H9, something like this. 9. Yep. Okay, so now we have to butanol. Let me see it again. So 1, 2, 3, 4 NHES. So okay. So now let's draw this. Okay, let's draw the structure. And again, it is asking us for the name. So the name will be, let me write it with red. The butyl will come from here. Butyl ethanoate. Ethanoate. So the butyl ethanoate will be the compound. From the ethanic acid CH3 COO. Then we have O, then the butanol part. So C comes here, C 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Yes. So this is how the structure of this will look like. So this is ester plus you and add H2O. This will be a simple reaction for this case. So this is how this ester will look like. Okay. So next part, moving ahead, question number 4. It says table shows information about some particles. State the number of neutrons in chlorine 3517. So again, we have this particle. This is the proton number, nucleon number. Nucleon number is actually sum of protons plus neutrons. Okay, nucleon number is actually the sum of protons and neutrons. So state the number of neutrons in chlorine. So number of neutrons, so if we have to find neutrons here, just simply minus 35 from 17, it becomes 18, 35 from 17, 18, 39 from 19, 20, again it's 20. So number of neutrons in this is 18. So number of electrons, so remember um, the number of electrons is same as number of protons. So the proton number is 17. So the electrons will be 17. But remember this negative sign. It's a negative sign. It means that it has gained one electron. So the number of electrons will be 17 plus 1, 18. So the 18 electrons will be there. So this one is coming from this negative sign. Then it says potassium 3919 is a full symbol for one isotope of potassium. Suggest one full symbol for one other isotope of potassium. So remember isotopes are have same number of same protons and different number of neutrons. Okay, so the potassium K, the lower number or the number of protons will remain the same. So 19. Neutrons will change. So you can add one neutron to the total value. So it can be 40 or it can be 38, 19. Can be anyone. You can use any. So I mean, your marking scheme has used this, so you can use this. Okay. So moving ahead, part D, it says describe how potassium ion is formed from potassium atom. So the potassium K positive, potassium loses one electron from its valence shell and becomes K positive ions. That is as simple as that. So potassium atom loses an electron and becomes K positive ion. Okay. Then it says potassium chloride is an ionic compound. Potassium chloride has a high melting and a high boiling point. Explain why potassium chloride has a high melting point. So again, it is an ionic compound. So ionic compounds are actually are held together in a lattice structure by very strong electrostatic forces. And in order to break these forces and break these strong bonds, a lot of energy is required. And therefore, the reason behind the high melting and boiling points. So let's write it down. Potassium chloride ions are held together in a lattice structure by strong electrostatic forces. So this is high amount of energy is required to break these bonds. Hence, high melting point. Okay. Then it says predict two physical properties of potassium chloride. So remember, these are ionic compounds, and this is a salt of potassium. and that means that it's potassium chloride. Sodium chloride is a highly soluble, water soluble compound. So soluble in water. Uh, Again, sodium chloride conducts electricity when in molten state. Same goes with potassium chloride, conducts electricity in molten state. Okay, so these are two physical properties that can always go well with any ionic compounds. So moving ahead, uh, question number 5, it says iron reacts with steam and with dilute sulfuric acid. The reaction between iron and steam is reversible. The forward reaction is exothermic. The equation is given. So 3 iron plus 4 water in gaseous form, iron oxide plus water in gas. An equilibrium mixture is formed when the reversible reaction happens in a closed system. Number 1, it says predict what happens to the amount of hydrogen. So remember, amount of hydrogen is in the product part. In the amount of hydrogen in the equilibrium mixture if the temperature is increased and the pressure remains constant. So remember, this question is related to Le Chatelier's principles. Le Chatelier's principles. So with Le Chatelier's principle, it's the first part. So we have to understand that the equilibrium has to be maintained. So if a temperature is increased, so temperature increases, what happens with the increase in temperature? So we say that forward reaction is exothermic. So increase in temperature favors the forward reaction, so exothermic reaction takes place. And what the whole reaction or what this whole system will do, the system will basically try to compensate that. In order to compensate that, the system will move in the backward direction to compensate the forward reaction or the reaction that is increased with the help of with the increase in temperature. So what the prediction? So with the temperature uh, sorry, so with the increase in temperature, the forward reaction increases, but what happens to the volume of hydrogen? So we have to, or the reaction moves towards the equilibrium. So in order to achieve the equilibrium, the backward reaction will increase. So if the backward reaction will increase, the volume of hydrogen will decrease. So our prediction is volume of H2 will decrease. Okay. So the explanation, the increase in temperature favors forward reaction to compensate this and establish equilibrium. The backward reaction increases till equilibrium is achieved. This decreases the volume of hydrogen. Okay, so this is how it will go. So next part, it says predict what happens to the amount of hydrogen in the equilibrium mixture if the pressure is increased and the temperature remains constant. So the pressure, remember, this is the equation that is given to us. So in this equation, we have one solid and we have one gas in the reactant side, and then we have another solid and a gas in the product side. So we have one gas in the products and we have one gas in the reactant side. And when we increase the pressure, the only or the effect primarily goes on the gases rather than the solids. So we see that the number of moles on the left hand side are equal to the number of moles on the right hand side. So 4 mole of gases are here, 4 mole of gases are here. So actually what will happen with the increase in pressure? Nothing will happen. So the amount of volume remains the same. The equilibrium will keep on existing as it was. So actually no effect uh, on the hydrogen amount. Okay, and the reason is the number of mole gases, the number of moles of gases on left hand side are equal to the number of moles of gases on the right hand side, right? So the equilibrium remains as it is. So this is how it is. So if the number of moles are the same, it will be the same. So if they are different, so the reaction will follow the direction which compensates the increase in pressure in this case. Okay. So moving ahead, it says part B, it says iron reacts with dilute sulfuric acid to make iron 2 sulfate. Construct an ionic equation. Remember, this is an ionic equation. So iron plus iron sulfate, I'm writing the general equation. Iron plus H2SO4, it gives us FeSO4 plus H2 gas. So the ionic equation, this as it is, iron comes from here. This goes here and this. So ionic equation Fe plus 2H positive, then comes Fe2 positive plus H2 gas. So this again dilute sulfuric acid dilutes this is aqueous. So this is iron. So this is solid aqueous. This is again aqueous solution and this is gas. So this is how the equation goes, and this is I have written the balance equation over here. So now it says that chemical test to confirm iron 2 sulfate is formed instead of iron 3. So remember iron 2 plus, the precipitates are green, and with iron 3 plus the precipitates are reddish brown. So we have to basically use either sodium hydroxide or ammonium hydroxide uh, to test that. So if the sodium hydroxide adding ammonium hydroxide or sodium hydroxide to the sample solution, uh, and the color of the solution turns green, it means that ferrous sulfate is there. And if the color of the solution changes to reddish brown, it means that ferrous 3 sulfate is there. So not one is ferric and one is ferrous. Uh, it would be, so we have to write, so add aqueous ammonium hydroxide. You can also use sodium here. Sodium hydroxide also can also be used to a sample solution. Dirty green precipitate of Fe, oh sorry, of iron 2 sulfate, iron 2 sulfate shows here SENC presence of, oh sorry, dirty green precipitate shows presence of iron 2 sulfate. And if the, remember, and if the precipitate is reddish brown, it shows the presence of iron 3 sulfate. This is a simple test that confirms our case. Then it says the aqueous iron 2 sulfate form is crystallized and make into hydrated iron 2 sulfate FeSO4.H2O. Calculate the relative formula mass for hydrated iron 2 sulfate. So relative formula mass of iron 2 sulfate. So remember iron, calculating the molecular mass of this formula, iron is 56 plus sulfur 32 plus oxygen 16, and there are 4 atoms. Then we have 7 multiplied by hydrogen is 2 plus 6 oxygen is 16. So if we add all of these together, it comes out to be 278 grams, or it's a relative formula mass. If you don't write grams over it, it's just 278. Okay, so this is how it goes. So moving ahead, question part 4. Question number part 4, it says a student uses 2.8 grams of iron to make 12.5 grams of hydrated iron 2 sulfate crystal. This is 90% yield. So see how this is 90%. So calculate moles of iron. So the number of moles of iron are actually 2.8 divided by 56. This is equivalent to 0.05 moles. And moles of FeSO4 crystals, 12.5 divided by 278, the mass, and this comes out to be what? This comes out to be 0.045 approximately moles. So the percentage yield, so actually 0.05 moles yield 0.045 moles. Oh, so 1 mole yield 0.045 divided by 0.05, 100, and this comes out to be 90%. So this is how this 90% comes. So calculate the mass of hydrated iron sulfate made from this if the yield is 100%. So if the yield is 100%, number of moles of FeSO4 will be 0.05 moles. So number of 0.05, so 278 multiplied by 0.05, this will give you what 13.9 grams, and that will be the mass of sulfur or the iron sulfate crystals if the yield is 100%. Okay. So now moving ahead, it says aqueous iron 2 sulfate. So remember, this is aqueous, is electrolyzed using graphite electrodes. So this is again aqueous solution. So we have these two electrodes, so positive, negative one. So something like this. So in this aqueous solution, we have iron 2 positive, we have SO4 2 negative, we have H positive, and we have OH negative ions. So predict the products of electrolysis. So in the electrolysis or in the electrochemical series, these two will take up precedence. So positive ion will move to the negative electrode, and the negative electrode is actually the cathode. So this is your cathode. So cathode will give you hydrogen gas, hydrogen gas. And at the node, OH negative ions will go here at anode, and oxygen gas will be released. Oxygen gas. So these will be the products of this reaction. So remember, the easiest ways to check, it is an aqueous solution. So it means that the iron sulfate is dissolved in water, and that is why we get the H positive and OH negative ions. Then part D, it says iron is extracted from iron ores in a blast furnace. Describe the essential reactions involved in the extraction of iron. So remember, this is a very important question. This is usually asked in the exam. So you have to be always up to the mark with this. So the key thing you have to remember over here is that the iron ore or iron ore or the iron oxide, for example, it is Fe2O3, is actually reduced in the blast furnace. So it is reduced with the help of reducing agents, and those reducing agents are high temperature coke, or that not Coca-Cola, that is carbon. I'm talking about high temperature carbon. And at high temperature, since the blast furnace is also takes air inside it, uh, and limited amount of air, so that also generates carbon monoxide. So carbon and carbon monoxide helps this Fe2O3 to reduce or reduces it to iron and form carbon dioxide. So these are the two key reactions. And other essential reactions are actually the production of carbon dioxide and carbon dioxide or coke and carbon monoxide in the blast furnace that eventually goes and helps to reactor. So describe this. So first step, basically, uh, the coke or carbon reacts with oxygen to form carbon dioxide. Then uh, this CO2 reacts with excess coke carbon to form carbon monoxide or CO. The CO or carbon monoxide reacts with iron ore, that is Fe2O3, to form iron and CO2 gas. The carbon or coke at high temperature in the furnace also reacts with Fe2O3 to form uh, iron and CO2 gas. Okay, and this is actually the processes that are involved. So if I have to write the reaction, so number one reaction will be carbon plus oxygen, carbon dioxide for manufacturing, then CO2 plus carbon to get carbon monoxide. Uh, then reaction 3, you can call it on the reaction 3 side, you have Fe2O3 reacting with CO. This gives you Fe plus CO2. So 4, so we have 2. You can always balance it. 2O3 6 and 8 6 8 oxygen, 4 carbon. Yes, now it is balanced, and this is together 4 iron. This and the other way is C2O3 plus carbon. You give Fe plus CO2. So we have 3, we have 1 O. Uh, so we have add 2 here. So iron will be 4, oxygen will be 6. So add 3 here, 3 here, something like this. So these are the uh, reactions. So all these reactions, this is important. This is actually the reaction of iron ore. Okay, and this takes place in the presence of catalyst. Again, I mean, this is all it goes. So this is how you have to write this, and this is for 3 points. So if you write these 3 reactions in this manner, I don't see any reason why the examiner won't be giving you the complete credit for this question. So this ends the section A for the this paper. Then comes the section B. Section B, it says we have to answer 3 questions, and we have to answer 3 questions in this section. And uh, in the space provided, the total marks 30. Then usually we are giving 4 questions here, and we have to select 3. And so I'm not fortunate enough, so I will be solving all these 3 for you. All this, sorry, 4 for you. So let's start. Question number 6. It says carbon monoxide, carbon and nitrogen monoxide are pollutants formed in car engine. Describe how nitrogen monoxide is formed in a car engine. Nitrogen, basically nitrogen and oxygen reacts together uh, in limited supply of oxygen gives you nitrogen monoxide, or we can also call it as incomplete combustion. Okay, so if we have a limited supply of oxygen, I mean, then we'll get carbon monoxide. Oh, sorry, nitrogen monoxide. Then we have carbon monoxide react with nitrogen monoxide as shown in this equation. This reaction is extremely slow at room temperature, but is much faster in the presence of a catalyst in a catalytic converter. Explain why this reaction involves both oxidation and reduction. So oxidation means gain of oxygen. So we can see that the carbon monoxide gains oxygen and becomes carbon dioxide, and nitrogen loses oxygen. Nitrogen monoxide loses oxygen to become nitrogen gas. So this involves both oxidation and reduction. So just write it as, so carbon monoxide gains ox oxygen to form carbon dioxide, This is oxidation, and nitrogen monoxide loses oxygen to form N2 gas. Okay, and this is reduction or loss of oxygen and is reduced. So you can always write carbon dioxide and is oxidized and is reduced. Okay, so this is how you can write it in a much better manner. Then it says the reaction between carbon monoxide and nitrogen monoxide is exothermic. Explain using the idea about bond breaking and bond forming why reaction is exothermic. So remember, bond breaking is endothermic process. It is endothermic process. For example, it absorbs energy. Okay, and bond forming is exothermic process and it releases energy. So we can just simply write that the energy released in bond formation is much more than the energy absorbed during the bond breaking process. Hence, the reaction is exothermic. Reaction is exothermic. Okay. Then part C, it says explain using ideas about particles why increasing the temperature increases the rate of reaction between carbon monoxide and nitrogen monoxide. So remember, increasing temperature increases the average kinetic energy of the particles. This increases the rate of collision between the particles of carbon dioxide and nitrogen dioxide, thereby increasing the probability of successful collisions, successful collisions above the activation energy, thereby the activation energy, full stop. This increases the rate of reaction. Okay, so key things: To remember, temperature increases the average kinetic energy of the molecules, or sorry, of the particles. The increase in average kinetic energy translates into the increase in the average rate of collision between the particles, and that translates into higher probability of successful collisions above the activation energy. Therefore, the overall rate of reaction increases. Okay, then it says question number it's the part 4 of question number 6. It says explain why catalyst increases the rate of reaction between carbon monoxide and nitrogen monoxide. So the rate of reaction, the catalyst lowers the activation energy. The catalyst lowers the activation energy required for the reaction. Okay, so this is as simple as that. Then it says explain using ideas about particles why catalyst in catalytic converter needs to have a large surface area. So large surface area basically increases the uh, uh, contact area, increase the contact area for the particles, and the more the contact area, or it means that more number of collisions per unit time, and thereby increases the rate of reaction. uh, so why the catalyst in catalytic converter needs to have a large area. So the larger area of the catalyst results in more contact area for the particles. This increases the number of collisions per unit time, thereby increasing the rate of reaction. So this is how it goes. So now moving ahead, question number 7. It says aluminum is an element in group 3 of the periodic table. Aluminum is used to make containers for food because it does not react with water. State and explain in terms of properties one other than large scale use of aluminum. So other large scale use of aluminum, transmission line cables, so cables, wires. You can also write aircrafts, cars, etc. So for wires, uh, this is because of good electrical conductor. For aircraft and cars, lightweight. The reason, whatever you want to write, lightweight is low density. So these are the reasons. Sorry. So then 7 part B, explain why aluminum does not react with cold water. So remember, aluminum has a tendency to make an native oxide or an oxide layer around itself, and that oxide is insoluble in water. And that oxide generally doesn't allow, it's not easily allow water to penetrate through it. So that is the only reason why it goes. So say uh, aluminum forms an oxide layer, uh, that is Al2O3, which is insoluble in cold water. Okay, and that is the reason why you can say that aluminum doesn't allow reaction with ox uh, uh, cold water. Then part C says describe the aid of label diagram the metallic bonding in solid aluminum. So remember the metallic bonding is actually between the ion cations and anions, or so actually there is a aluminum positive ions, and then there is a delocalized sea of electrons that is around there. So and they are densely packed, very strong electrostatic forces. So this not so yes, these are, say for example, positive ions of aluminum, and these are the delocalized electrons you have, and there is a sea of these delocalized electrons, lots of them. So these are localized electrons, positive ions. So, so if you have to write it, is the positively charged aluminum ions are closely packed and surrounded by a localized sea of electrons. The aluminum metal is held together by strong forces of attraction between the positive ions and the localized sea of electrons. Okay, so this is how you can describe the metallic bonding in the uh, aluminum. So then it says aluminum is manufactured by electrolysis of aluminum oxide dissolved in molten cryolite. Write ionic equations at cathode and anode. So aluminum oxide is, so remember this is in molten form. So this is aluminum Al2O3. So the ions are Al3 positive and O2 negative. So at cathode is negative electrode. So positive ions will go over there. Aluminum 3 ions will go there. They will gain electrons and will become aluminum. Okay. And that will be in liquid form. At anode, the negative ions or oxygen to negative will come. They will lose electrons, 4 electrons, and it becomes oxygen gas, O2. Again, this is in gaseous form. So these will be the two equations for this, or the two ionic equations. So remember, we have to write the ionic equations for this. So this will be the two ionic equations for this case. Then it says part E, a sample of 2.43 grams of aluminum is reacted with 50 centimeter cube of 2 mole per dm cube of sulfuric acid. The reaction equation is shown. Show by calculation that aluminum is in excess. So just first of all, number of moles of aluminum. So the number of moles of aluminum, 2.34 grams divided by 27 is the molecular mass of aluminum is 0.0866 moles. Okay, and then we have to calculate number of moles of H2SO4. So these are the two products that are available to us. So number of moles, remember 50 centimeter cube. So 1 decimeter cube is equal to 1000 centimeter cube or 1 liter actually. So, so 50 centimeter cube is the volume and 2 mole per 1000 centimeter cube. So the number of moles are equal to 0.1 mole. Okay, so these are 0.1 mole is the number of moles for the you can say H2SO4. So remember, so from the equation, if we see here, so we have 3 moles of H2SO4 reacts with 2 moles of aluminum. So if we have 1 mole of H2SO4, that will react with 2 by 3 moles of aluminum. And if we have 0.1 mole of H2SO4 as we have here, that will need 2 by 3 multiplied by 0.1, and that is equal to 2 by 3. So that will be equal to 0.06666 moles of aluminum. So these are the number of moles of aluminum that we need for the reaction. And how many we have? We have this many. Difference is 0.0866 minus 0.0666, and that difference is approximately equal to 0.02 moles excess of aluminum. So if 0.02 moles excess, it means 0.02 multiplied by 27. This is equivalent to 0.54 grams of excess aluminum that is available. So if you are going, or if you're going to say anything like this, 0.02 moles of excess aluminum or 0.54 grams of excess aluminum is available, you will be good for this, I mean, analysis or showing that the aluminum is in excess. Okay. So moving ahead, question number 8, the second last question, it says alkenes are homologous series of unsaturated hydrocarbons. Name the alkene that has only 3 carbon atoms. So alkene with 3 carbon atom is propene, 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 and this is C3H6. So remember alkenes general formula CnH2n. Then it says draw a structure of an unbranched and a branched alkene. Show all atoms and all bonds in each structure. So unbranched against C3H6, that is the easiest to draw. C3 carbon CH 1 2 3 1 2 1 1 2 3 4 5 6. So this is unbranched one, or and a branched one I mean, you need to have at least 4 or more. That will give you a better branching. So if you have to draw it, I'll draw it with a blue one. So C double bond C H H, something like this. Then CH3, CH3, and then CH3. So this is a branched one version of 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 1, 2, 3, 4. So C4H8. Okay, so this is how a branched alkene will look like. Okay, now moving ahead, we have to write a chemical test that distinguishes an alkene from an alkane. So again, saturated from unsaturated. Uh, the chemical test is add aqueous bromine to a solution. So add aqueous bromine to a solution. Result with alkene. So with alkene, uh, the color change from orange to colorless. From orange to colorless. And with alkene, no color change occurs. Okay, so with alkene, the aqueous bromine is or the is it becomes colorless or the loses its color, and whereas the no color change with the alkanes are there. And this is a simple test that is there in the literature for it, and it just simply basically says the saturation or unsaturation test for a saturated or unsaturated compounds. Then it says part D, alkenes are manufactured by cracking of long hydrocarbons. The equation for cracking of C14H30 is shown. Give two reasons why cracking of long hydrocarbons is important. So again, cracking of long hydrocarbons is a source of gasoline or fuel for us, and also extensively used in making polymers, and is also an industrial mechanism to manufacture hydrogen or to create hydrogen gas. So why the cracking of long chains? So the cracking process is a source of fuel, gasoline. It is also used for making polymers and hydrogen gas on commercial scale. Okay, that is why it is important. Then it says compound X contains 85% carbon by mass and 40.3% hydrogen by mass. Calculate the percentage, composition data, and the empirical formula of X. So carbon and so in the analysis, let's see, let me see here. So we have carbon, we have hydrogen. So percentage carbon 85.7, hydrogen 14.3. So number of moles 85.7 divided by 12, 14.3 divided by 1. The number of moles comes out to be 7.14. This comes out to be 14.3. And divide by least So this becomes 1 and this becomes 2. So percentage ratio or the empirical formula from this side is CH2. So the empirical formula becomes CH2. And now if we are going to see this equation, C14H13, so C14H30, we have 2x plus C8H18. So now this X, so actually X will be, you can say CH2 or any factor, or you have to multiply N with it, plus C8H18. So balance this number of carbon atoms first. So carbon atoms are 8, 9, 10, and there are 14. So if I have 3 here, 3 into 2, 6, 6 plus 8, 14. So yes, so it would be C3H6. This will be the molecular formula of the compound X, C3H6, and that comes just by simply balancing this equation in your case. Okay. So moving ahead with our last question, question number 9 for this exam. It says ammonia or NH3 is used to make nitrogenous fertilizers. Ammonia is so part A, it says ammonia is manufactured using reversible reaction between nitrogen and hydrogen. It says construct equation for this reversible reaction. So we have to write an equation. So remember, this is a reversible reaction. So always use this sign, and ammonia NH3. Again, this is in gas, this is gas, this is gas. So now we have to balance is N2. So if we have 2 here, N is balanced, 2, 3, 6, 2 here, so 3 here. So this is how this reaction goes. Then ammonia is part B, ammonia is used to make soluble salt, ammonium nitrates. Remember, all nitrates are soluble. Name the acid that reacts with ammonia to make ammonium nitrate. Simple, nitric acid, uh, or HNO3 is a simple acid that will react to produce ammonium nitrate. Then it says calculate percentage mass of nitrogen in ammonium nitrate. So percentage mass of nitrogen, NH4NO3. This is the formula. So calculate MR. Molecular mass of this, so molecular mass nitrogen is 14, hydrogen 4 multiplied by 1 plus again nitrogen 14 plus 16 into 3 oxygen. Overall it becomes 80. All the nitrogens, percentage of nitrogen, it comes out to be, so this is 14 and this is 14, so 14 plus 14 over 80, so 28 by 80 into 100, this comes out to be 35%. So percentage by mass in ammonium nitrate, 35% is there. Then part C, it says nitrogenous fertilizers such as ammonium nitrate leach from the farmland and cause water pollution problems in rivers and lakes. Name the process caused by this type of water pollution. Then this is eutrophication. Eutrophication. Okay, so that is an environmental hazard that happens because of this. Then it says explain why this type of water pollution is a problem. This type of water pollution problem is increased when nitrate fertilizers are used instead of other fries. So remember, nitrates are highly soluble in water. So remember, nitrates are highly soluble compounds, highly water soluble compounds. You can call it as highly water soluble compounds. This results in contamination, contamination of water with the use of these this contamination of water by use of these fertilizers. Okay. Moving ahead, part D, it says a farmer adds ammonium nitrate, NaNH4, NO3 to the soil. The farmer then adds calcium hydroxide to the same soil. State the purpose of adding calcium hydroxide. So calcium hydroxide is actually added to balance or to reduce the acidity of the soil and basically raises the pH level. So to reduce the acidity of the soil and increase the pH levels. Okay. Then it says part D, it says construct the equation for the reaction between ammonium nitrate and calcium hydroxide. So ammonium nitrate is NH4NO3 plus CaOH uh, becomes calcium nitrate 3 plus ammonia plus water. And we are balancing it. So it is something like this. Okay. Then using your equation, explain why the ammonium nitrate fertilizer is less effective. So remember, this is gas, this is liquid, uh, this is solid, or this is a soluble solid calcium nitrate. Uh, uh, why is less effective after calcium hydroxide is added? So why affected? Because the ammonia gas is released uh, which was or which is required by the soil as fertilizer in released in atmosphere, which is used there. This degrades the effectiveness of the fertilizer. Okay, so now what this reaction is doing, that this reaction is actually releasing the ammonia from the ammonium nitrate into the atmosphere, uh, thereby decreasing the nitrogen content that is absorbed by the soil, or the value or the amount of ammonia that is very rich in nitrogen, or is actually required as fertilizer material by the soil, and that is which was earlier present for the soil when ammonium nitrate was used as fertilizer. But when calcium hydroxide was added, that ammonia that was present in the ammonium nitrate is released in the atmosphere, thereby decreasing the effectiveness of the fertilizer. So this is how you're going to answer this question. Uh, so so now, I mean, this is the end of this exam. So I know that you'll be giving your exams in a couple of days, and I wish you all the best for your exam, and I hope you succeed, and I hope this video has helped you in preparing much better for your exam. Again, best of luck. Take care. Bye-bye.